This is Math 151, and we're in Section 1B. This is Part 3. We have a couple more numerical limits to take a look at. In Example 3, we're looking at the function x minus 3 over x squared minus 9, and we have a few limits to do. First one is, what happens as x approaches 3? I know for sure when x is 3, I would have 9 minus 9, or 0, in the denominator. So certainly the y value doesn't exist when x is 3. And so I'm going to pick values that get closer to 3 from the left, and then also closer to 3 from the right. So from the left, I'll pick 2.9, 2.99, 2.999, again, kind of our protocol, getting closer by an order of magnitude each time. And then 3.1 on the right, as well as 3.01 and 3.001. And then we'll just calculate the y values that go with that. We've done this several times now in Desmos, or you can use a graphing calculator. So I'm just going to go ahead and fill those in without taking us to the site this time, just to save a little bit of time. And so there those numbers are. As x approached 3 from the left and from the right, take a look at what's happening to the y values here. We've got 0.16, 0.166, 0.1666. The pattern, again, always look at the pattern you're establishing. The pattern seems to be we're trying to go to 0.16, and there's one extra 6 each time. So I think we're trying to get to 0.16 repeating. Or if you grab your calculator, if you're not sure, and change that into fraction mode, that would be 1/6. I'm seeing the exact same pattern from the right-hand side. The number of 6's seems to increase the closer we get to x equals 3. So once again, I believe y is trying to approach 0.16 with the 6 repeating, or as a fraction 1/6. So I think we're going to go with a limit of 1/6 here. Before we lose the space and shove our paper up here, let's talk about what this means. This is one of these where the function does not exist, but there is a finite limit. This should be a hole in the graph. When x is 3 and y is 1/6. All right, the next one, x is approaching negative 3. And once again, I'll notice that that would put 9 minus 9, or 0, in the denominator. So certainly, this does not exist when x equals 3. I need to choose values then that approach negative 3. Again, be a little careful with the negatives. On the left side, we'd have negative 3.1, and so on. And on the right side, we would have negative 2.9, and so on there as well. And again, we've plugged these into the calculator enough times. I'm just going to go ahead, or plug them into Desmos enough times. I'm going to go ahead and assume that you know how to do that, and I'm just going to fill those values in for us. And there they are. For the y values, I have negative 10, negative 100, and negative 1,000 as I approach from the left. This seems as though the y values are getting larger and larger, but in the negative direction. So I'm thinking that tells me y is going to negative infinity. And same thing on the right-hand side, except this time I'm going to positive large numbers. So coming from the right, I think y is going to positive infinity. Since the y values are becoming infinite, this tells me I have a vertical asymptote at x equal to negative 3. The limit itself does not exist. Since the limits from the left and the right were different, one's negative, one positive, but I do have a vertical asymptote at x equal to negative 3. What we're starting to see here now is telling exactly what the limit says about the graph. before we actually do the graph. And this is something that I'm going to ask you to get used to. I'll often ask you to do things like this on homework. All right, the last two have to do with what happens as x approaches negative infinity and when x approaches positive infinity. So x goes to negative infinity. I'll pick negative 10, negative 100, and negative 1,000. And when x goes to positive infinity, 10, 100, and 1,000. And once again, I'm just going to go ahead and fill those values in for us. And there those are. As we approach negative infinity with our x values, notice the y values seem to be getting closer and closer to 0, right? That's somewhere around the neighborhood of negative 1/10, negative 100th, negative 1,000th. There are more zeros after the decimal place each time, establishing that pattern. So I do believe that y is going to 0 here. And kind of the same thing here. More zeros after the decimal point each time, the y value does seem to be approaching 0. So both on the left side, the end behavior goes to 0, and on the right side, the end behavior goes to 0, seeming to indicate both a limit of 0 for both of these and a horizontal asymptote. We've got to approach y equals 0 on both ends. All right, let's try to incorporate all of that information into a graph. So I'm going to start by defining my asymptotes. We were predicting a vertical asymptote at negative 3. Let's see, I think I'm going to go with, what do I need here? Yeah, let's go with 2, or 1, 2, 3, 4, 5. And negative 5, 5, and negative 5. So my vertical asymptote at negative 3 would be right here. And my horizontal asymptote is at y equals 0, right on the x-axis. All right. Additionally, we knew that we were supposed to have a hole in this graph when x was 3 and y was 1/6. That was the very first limit we did. So 1, 2, 3, 1/6, but less than a half, somewhere around here. There's going to be a little hole in this graph. And I can now go ahead, I could use the calculator or Desmos or whatever to fill in the blanks, but I can actually even tell a little bit more. Notice on my vertical asymptotes, it's just one of them, my vertical asymptote. Notice that I know as I approached negative 3 from the left, this went down to negative infinity. So I would be predicting that coming in from the left, this goes down. So I'm going to start up here near the horizontal asymptote and go down along the vertical. Approaching negative 3 from the right, my limit was positive infinity. So I should be going up along the vertical asymptote on the right-hand side. And then I'm going to go ahead and come on over, and I'm going to make sure that I kind of aim for that little hole in the graph. I'm going to skip over that, and then just stay really close to that horizontal asymptote. And there we go. If I go ahead and pop over to Desmos, I've got it graphed for us here, same window, negative 5 to 5 on both axes. And you can definitely see that vertical asymptote at negative 3. Again, if I wanted to, I could actually graph it as x equals negative 3. In fact, if you kind of hold this down, it'll even allow you to make it dotted. And maybe this one. Yeah, I like that better. There we go. And so I can really see that it's an asymptote. Play around with this thing, change the color. There. All right. And then I can also graph in my horizontal asymptote, which of course is y equals 0. There. And now I've really identified the asymptotes on the graph. You can clearly see them as dotted lines like we like to do them. The one thing that's not clear on this graph is notice that at x equals 3, there's no little hole in the graph. Now if I type in x equals 3, Desmos admits that the graph is undefined there. It just doesn't show us the hole. If you wanted to generate that with Desmos, you actually can do it. You can tell it, graph the point 3/16. And there it is. And I can put a little hole in it right there with the style. If I want to, I can even have Desmos label it for me. There we go. It'll label it with the decimal form, but there it is. So you can create really nice graphs with these things, and I'm telling you that because there may come a time that I'll ask you to produce things like this for me and hand them in. So some nice little techniques for producing really nice graphs where you could show your understanding by actually clearly showing the asymptotes, showing the holes, things like that. All right, so this brings us to our last example. This last one is a piecewise defined function. And so our function f of x is defined right here. And notice that where this piecewise function changes from one formula to the other is at -3 and again at 0. So that's where we're going to look for the limits, at -3 and at 0. And since right now we are using a numerical method, I'm going to approach this exactly the way that we did before. I'm going to say if I want to approach -3, let's approach from both the left and the right. So on the left side of -3, getting closer and closer, and on the right side of -3, also getting closer and closer. Now, I'm going to be a little bit careful here. On the left-hand side, all of these x values are certainly less than -3. So when I plug these in, being less than -3, I'm going to use the piece of the function x squared minus 5 to generate these y values. These numbers are all bigger than -3. They're specifically between -3 and 0. So I'm going to use the function x plus 2 to generate the y values here. Notice right at -3, the equality is here, so I can do that one in my head. That would be 9 minus 5. That's definitely going to give me a 4. So something a little bit different. Usually we've been seeing undefined for our limiting the value that x is approaching. This time we actually have a y value. All right, so again, I'm just going to go ahead and fill those in for us. Not difficult to generate those values. And there they are. Approaching from the left, the y values start with 4 over time, and then notice there's a 0 after the decimal here. 2 zeros there. Pattern's a little weak at this point, but I think we have enough to say it looks like we're trying to get more and more zeros after the 4 each time. So I believe this is enough to say y is approaching 4. Coming into -3 from the right, notice these y values seem to be getting closer and closer to -1. So our limit doesn't exist because coming in from the left and the right gives me 2 different values. But what I can say is that the limit, as x approaches -3 from the left for this function, is 4. And the limit as x approaches negative 3 from the right for this function is negative 1. So this is going to be a jump on the graph. All right, we'll do something very similar to allow x to approach 0. Let's see, when x is actually equal to 0, the equal 0 is right here. So if I were to plug 0 in for x, 0 plus 2 would give me 2. All right, let's approach from the left and the right. Oops. 1 too many zeros there. Let's just make that point 0, 1. Okay, and again, well actually first of all let's just think about which of these three pieces of the function we're plugging things into. Here we have these x values are all between negative 3 and 0, so we'll use x plus 2 for these. And here these x values are all greater than 0, so we're going to use y equals 2 cosine x for those. Make sure you are in radian mode when you do your cosines, and other than that you can just plug these into a calculator or Desmos to get the values. And again, I'm just going to jot those down for us this time. There they are. Coming in from the left, these numbers, those 9s are trying to keep on going. Looks like they really are getting closer and closer to 2. Coming in from the left. And coming in from the right, again, there are more and more 9s after the decimal point each time. So that 1.99999 is once again trying to get very, very close to y equals 2. So this time, the limit from the left and the right are the same, and this limit does exist, and its value is 2. Notice that's the same as the value of the function when x is 0. So I'm expecting this to be a continuous point. The function value and the limit value are the same. All right, so let's see here. A few things that we can put into our graph right away. Let's put the values in for the jump. When x is negative 3, we'll have 1 point at negative 3, 4. And let's see, what are my values looking like? I'm going to do the same thing. I'm going to use every other tick mark as a whole number 1. So that's 5 and negative 5. And we'll do the same thing here. So when x is negative 3, we'll have 1 point at negative 3, 4, and another point at negative 3, negative 1. Now notice negative 3, 4 is actually a point on the graph. So this time I can make that a solid dot at negative 3, 4. But negative 3, 1 is going to be a piece of my limit, but it's not a solid dot on the graph. 0, 2 is a continuous point. I might as well plot it, although nothing particularly special is going to happen there. All right, so let's see. It looks to me like we're connecting several pieces. When x is less than or equal to negative 3, we have a piece of the parabola, x squared minus 5, and we're coming towards that point negative 3, 4 from the left. So let's see. The full parabola, of course, would be all the way like this. This is just a piece of it. I'm just going to draw a slightly curved line coming in there. Then, between negative 3 and 0, we have just the straight line x plus 2. So approaching negative 3 from the right, we were down here at negative 3, 1. Then we just have a straight line connecting us to that 0, 2. And then finally, to finish out, anything greater than 0, we're at 2 cosine x. We know that's just a cosine curve with an amplitude of 2. Let's see, it would have 2 pi as its period, so let's go 2 pi, we'd be back right around here. At 1 pi, we're down here at negative 2, just to give me an idea of how to draw this thing. And I'll draw the beginnings of a cosine curve there. But you can see how the jump shows up in our graph, and then the fact that these two pieces matched up from the left and the right made that a continuous point. All right, that brings us to the end of section 1B.